For this part of the lesson, we're going to look at an example of a single server system, and it's problem 5.6 on page 217 of your textbook. And again, this is the Peachtree Airport problem. And let me go ahead and read this problem. Peachtree Airport in Atlanta serves light aircraft. It has a single runway and one air traffic controller to land planes. It takes an airplane 8 minutes to land and clear the runway, exponentially distributed. Planes arrive at the airport at the rate of 5 per hour, Poisson distributed. Then it has 4 different questions, and then I will add a 5th. But here's the 4, and we'll work through each one individually. Part A, determine the average number of planes that will stack up waiting to land. Part B, find the average time a plane must wait in line before it can land. Part C, calculate the average time it takes a plane to clear the runway once it is notified the airport that it is in the vicinity and wants to land. And D, the FAA has a rule that air traffic controller can, on the average, land planes a maximum of 45 minutes out of every hour. There must be 15 minutes of idle time available to relieve the tension. Will this airport have to hire an extra air traffic controller? So those are our 4 questions. So let me go back, and we're first going to work problem A. And the question is, determine the average number of planes that will stack up waiting to land. So for each one of these types of problems, you need to ask yourself, which operating characteristic do I need to select to answer the question? So let me read it again. Determine the average number of planes that will stack up waiting to land. And again, there's key words. If you, as I read the problem, hopefully you heard the word number. What's the average number? And so for part A, it's going to be one of these 2 operating characteristics, either L or L sub Q. So the question then becomes, which of these 2 operating characteristics, which one is the correct one? And it says again, determine the average number of planes that will stack up waiting to land. And this requires a bit of understanding how the system operates, and hopefully you're able to anticipate, and I'll explain this when we get to the next slide, but the correct way to approach and formula that we need to use is L sub Q, not L, because these planes are customers and they're waiting in line. So we need to calculate the value of L sub Q for the single server situation. So let's look how this works. First of all, we want to make sure that we understand the system. And again, for our Peachtree Airport, and you'll have to pardon my graphics here, but we've got a single air traffic controller. This is the control tower. And we have a single runway. These are the runway lines. So we have a single runway. And then we have airplanes. Here's airplane number 1, airplane number 2, and then we have other airplanes that are possibly waiting to land. Right, so we have, you should ask yourself, how many servers do we have? Well, certainly in this case, we only have one air traffic controller, one runway. So this is a single server system. There is only one line because all of these planes are waiting in order to land. And so this is how the system operates. The next thing you want to ask yourself is, well, what's the arrival rate of our aircraft, and what's the service rate of how fast can we serve these aircraft? Well, for the arrival rate, you're told that the arrival rate is 5 aircraft. I'm going to abbreviate just with A, aircraft per hour. That's the arrival rate, 5 aircraft per hour. And for the service rate, you're actually not told the rate. You're told that it takes 8 minutes to land and clear the runway. Well, so then the question becomes, what is the service rate? Now here comes one of the first important points. And this is the same, similar to what we talked about when we talked about the Poisson and the exponential distribution. The arrival rate and the service rate, they must be in the same time dimension. So if we're going to use hours as the arrival rate, we also need to express our service rate in terms of aircraft per hour. And so you need to ask yourself your question. If it takes 8 minutes for let's say this is the airplane that's landing here, this is number 1. If it takes 8 minutes on average for this one to land and clear the way, how many aircraft can I serve per hour? So I want you to think about that for a minute. Well, hopefully you know that there's 60 minutes per hour. And if it takes 8 minutes, then in those 60 minutes, there's 8 aircraft that can be landed. So the number of aircraft per hour is 7.5 when you do that arithmetic. So our service rate is 7.5 aircraft per hour. Now, the next thing I want to discuss, and this is the next important point, is the following. What's the relationship between lambda and mu? And I'm going to ask you, is lambda less than or equal to, or greater than or equal to mu? What's this relationship? And one of these has to be true. Well, hopefully you will see that what has to happen is that lambda has to be less than or equal to mu. In other words, as is in this case, in other words, you have to be able to serve at a rate that's faster than the customers arrive. Said alternatively, mu has to be strictly greater than or equal to lambda. The service rate has to be larger than the arrival rate. And similarly, the service rate has to be, or excuse me, the arrival rate has to be less than the service rate. Okay, so that's another important factor. So if the time dimensions don't match, or if this relationship isn't satisfied, then right off the bat, you have an issue with solving the problem. All right, so now let's go and solve our problem. We know that lambda is 5. We know that mu is the service rate 7.5 per hour. And so now what we need to know is what is L sub Q. And if you look at your textbook, there's a table on page 215. Under the single server model, you're going to see that L sub Q is going to be lambda squared over mu times mu minus lambda. And that's the formula. And so now we're just going to take our information that we have from above, substitute in, and do the calculations. So lambda squared is 5 squared. The denominator is mu, 7.5 times 7.5 minus 5, mu minus lambda. And of course, we're going to do our arithmetic. The numerator is 25. The denominator, once you do all of the calculations, is going to be 18.25. And LQ, when you do the division, is 1.33 repeating. And so now at this point, you want to ask yourself, well, what is 1.33 what? And it turns out that this is 1.33 aircraft, just the aircraft, just our customers. So we have on average 1 1/3 aircraft that are circling, waiting to get into the airport. Now, what is 1/3 of an aircraft? And you have to remember this is an average value. So if you come up to the airport, 1 hour there'll be 1, next hour there'll be 2, next hour there'll be 1, next hour there'll be 1. If you take that average is 1 1/3 aircraft waiting, circling, waiting to land. Okay. Now let's go ahead and look at the second part B and then part C together. So part B says, find the average time a plane must wait in line before it can land. So I'm going to skip back up. What's the average time a plane must wait before it can land? So again, now the key word is time. What's the time? So it's either going to be W or W sub Q. Find the average time a plane must wait in line before it can land. So before it can land must be the time that it spends in line. So here we're going to look at the value, calculate the value of W sub Q. All right. And so for part B, change colors, we want to calculate the value of W sub Q. And there's actually 2 ways to do this. W sub Q is L sub Q, and divided by lambda, or it's going to be lambda over mu times mu minus lambda. And we actually already know some of these values because we know lambda is 5, that these haven't changed. And then the denominator is going to be the same as it was previously, which is 18.75 when you do substitute in and do all the arithmetic. And then when this comes out, this value is 0.266 repeating. That's a 6. Now, again, ask yourself, what is 2.66? And again, W sub Q is time. And so this time is 2.66 hours. So it's 0.26 of an hour. So if we multiply this by 60 minutes per hour, that's going to tell you that this is actually going to be 16 minutes. So why is this important to know? Because if this is the average, then thinking in practical terms, an aircraft that's coming to the Peachtree Airport needs at least 16 minutes of fuel on average to be able to complete the landing process. Otherwise, there's going to be an emergency. So that's part B. Now for question C, how are we going to calculate this result? And question C is as follows. Calculate the average time it takes a plane to clear the runway once it is notified the airport that it's in the vicinity and wants to land. So calculate the average time. So again, we're going to be on the time category. And so it's either going to be W or W sub Q. And in this case, we're going to calculate the value of W because the time it takes for the plane to clear the runway once it's notified the airport that it intends to land, that's the time in the whole system. And so in this case, W, and again, going to page 215, W is 1 over mu minus lambda. And again, if you remember, we haven't changed, so mu is 7.5. And lambda is 5. And so this is 1 over 2.5, which is, once we do the arithmetic, is 0.4. Again, what 0.4 what? And again, this is 0.4 because our lambdas and mu are expressed in terms of hours. This is 0.4 hours. Well, again, how many minutes is that? Well, if we multiply this by 60, 0.4 times 60, this is 24 minutes. Now, there's something that I want you to notice here. What did the original problem statement say? And what's the relationship between these two numbers? WQ, this is WQ, and our airplane, it took the aircraft 16 minutes on average in line, or waiting to circle and waiting to land. And then it took total time in the system from until it cleared the runway was 24 minutes. What's the difference here? The difference here is that 8 minutes, which is that 8 minutes of service time. So that's good. You would hope you would see that. This is 8 minutes. You would hope that you would see that would be the case. Okay. Now let's look at D. This one's a little bit more challenging. The FAA has a rule that an air traffic controller can, on the average, land planes a maximum of 45 minutes out of every hour. There must be 15 minutes of idle time available to relieve the tension. Will this airport have to hire an extra air traffic controller? So then the question you have to ask yourself is, which one of these operating characteristics do we need to use to answer the question? Well, if you think carefully about it, the FAA has put a cap, a limit on how busy the air traffic controller can be, or how much percent of the time that air traffic controller is busy. So in this situation, we want to calculate the value of rho. And in terms of our problem, what's the air traffic controller, the FAA standard? So the FAA has said that the server utilization, rho, has to be less than or equal to 45 minutes. At most, it can be 45 minutes out of every hour. So that is so 75% of the time busy. So then the question is, in terms of the problem, when would Peachtree have to hire another air traffic controller? If this is the standard, so if rho is greater than or equal to, if there's more than 75% busy, then hire. Let me write it, if. So then the question is rho more than 75% or not? What do we do? How do we calculate rho? Well, it turns out we're in luck, because that's maybe one of the easiest operating characteristics you can't calculate, at least for the single server case. Rho in this case is this parameter lambda divided by mu. And those have not changed. Lambda is 5, and mu we're substituting back in 7.5. And this turns out to be, when you do the calculation, 0.66 repeating, or 2/3. And so rho, in fact, is less than or equal to 0.75. So that's, in terms of FAA, that's good. And so no, we do not, no higher. We're in good shape. Okay. Any questions about that? If there are, please get with me. Now I'm adding one more problem that's not in your textbook, but it's related to our Peachtree problem. And this is the question I want to add to this. What's the chance that at least 2 airplanes will be circling the airport waiting to land? And again, there's the key word, chance. So you know that it's a probability. And now what I want you to think about is what does this, there's at least 2 airplanes circling the airport. There's some other keywords in here. And the first one is, first 2 keywords are at least. And then of course there's 2 airplanes circling. And what does that mean in terms of our information or quantity that we need to calculate? Certainly, if we go back to this will be the one of the 2 that we haven't calculated, but we're going to need to calculate. It's going to be somehow related to the probability of customers in the system, because this is we've asked about the chance. So now we need to express this problem in terms of customers in the system. So let me see if I can describe this, help you out. Here's our one runway. And what does it mean for two airplanes to be circling? What does that mean? How many planes, if two airplanes are circling, how many are in the system? Well, here's one airplane, here's two airplanes. Is n equal 2? But ask yourself, what are these planes doing? In actuality, n does equal 2 in this example, but what's plane number 1 doing? This plane is actually now in the process of landing. This plane number 2, is in the process of circling. So in this case, this does not satisfy two airplanes circling. So in fact, what we want to know is there actually has to be 3 airplanes in the system. And now when there's 3 airplanes in the system, now 2 are circling. So it's not n equal 2. What we want to look at too is the situation where we have at least 3 in the system, because 1 is landing and 2 are circling. Okay, so one of the probabilities that we do want to calculate is clearly P sub 3, because that's the probability that there's 3 aircraft in the system. And that's the case where there's exactly 2 or equals to exactly 2 airplanes circling. But what does this term at least mean? Because then we could have 3 airplanes in the system, we could have 4, we could have 5, we could have 6, all the way out to an infinite number of airplanes. And so that would mean we would need to calculate this probability P3 plus P4, the case where 3 are circling, plus the case where 5 are circling, plus the case where 6 are circling, so on and so forth, all the way out to P infinity. And that's a lot of work. But by knowing our probability laws, this is going to also be equal to 1 minus the probability that there's none in the system plus the probability that there's exactly 1 in the system landing plus the probability that there's exactly 2 in the system, 1 landing and 1 circling. And so now we can, hopefully you can see, it's much easier to actually calculate this value. And so we've got to calculate 3 terms and then 1 subtraction. And so this is going to be, and I'm going to list for you to work at this point, come up with the solution, but the formula for P sub n in each case, P sub n is, and if you look on page 217, it's going to be lambda over mu, that quantity raised to the nth power, times 1 minus lambda over mu. And so we'll take this formula and we'll calculate this value. We'll substitute in n equals 0, for n equals 1, and for n equals 2 into that formula where we know that lambda is 5 and mu equals 7.5. And that once we do that calculation, that'll give you this value. So I'm going to leave that with you to solve. If you have any questions, please don't hesitate to contact me and we'll work through this. And now there's one more slide. And here are the formulas, all of those operating characteristic formulas. Now, one of the things I haven't said about this, and I will, is that if we were in a different setting, you would actually have to derive and calculate these values if we were in a more of a math class or in a stochastic processes class. But for our purposes, you need to take all of these formulas as well as the truth, because they are correct. They're well known and well used. And so again, I do not expect you to memorize these formulas. That's why everything that we do is open book and open notes. And I would encourage you to be familiar with them so that you understand what they are, what they stand for, but you do not need to memorize those, because everything that we will do in this class is open book and open notes. So hope this makes sense. Hope you understand, hope it's clear. If not, again, happy to help. Just let me know.